Tom Harding is a Bitcoin open source contributor and has been a Bitcoiner since 2011, a developer since 2014, and currently maintains the GitHub repository for the Bitcoin XT implementation. Today, Tom Harding presents the Scalable Payment Verification Network.
Hello, Bitcoiners. I'm Tom Harding. Thank you to the OnChain Scaling Conference for giving me the chance to present today. I'm going to present an idea that I first talked about at the Satoshi's Vision Conference with some of the fine folks from Bitcoin Unlimited in September of 2016. It's a little bit changed from there, but not much. The title of this talk is Scalable Payment Verification Network. This is something that doesn't exist yet. It's an idea. And by the end, hopefully you'll understand what I mean by it. The basic question is, how do we scale the things we know how to scale in order to achieve better scale without a lot of new ideas or cryptography that is untested? Have we really pushed the limits of what we know so far? And particularly, I want to focus on a technology that a lot of us may take for granted, which we call SPV. It means slightly different things in different contexts, but I want to talk about that and some improvements we could make to it, and then go on to the network improvements that could lead to a lot more scaling on-chain. Satoshi described SPV in his white paper. It is Satoshi's decentralized scaling solution. SPV is where your wallet stores a highly pruned blockchain, just the headers, just your own transactions, and the Merkle proofs that connect both of those things. The security derives from the confirmations as the chain grows and as work is posted into it. Your SPV wallet talks to Bitcoin nodes. It doesn't talk to proprietary servers or third-party APIs. It talks to the Bitcoin network directly, which is very cool. And the user has full control of his keys, so it's not a web wallet. This is something that we want to keep, these properties. But SPV does have vulnerabilities. Two major ones are that the mining and full node network could hard fork without you knowing. And another, this hasn't happened yet, but it could happen. Another is that your network provider could omit information. Also hasn't happened yet. But nevertheless, SPV is the focus of almost, I would say, derision in certain circles. In the presentation copied here, it was called a toxic light client and compared to mercury poisoning. There's also privacy concerns related to bloom filters and the way they're used today, which is why you'll sometimes hear a white paper SPV client distinguished from what's in use today. But the fact is, as of now, the market's accepted these risks. Millions of SPV wallets are in use every day, and they run on your mobile phone. So what they achieve is pretty amazing. We can make it more secure and more scalable. It's actually kind of surprising some of the basic things that have been left out that can be added in. Satoshi described something in the white paper that he called fraud proofs. And what he meant by that in the white paper is that the node would receive alerts when a remote node detects an invalid block. And his suggestion in the white paper is that the light client should download the full block. There's a couple problems with that. One is that an SPV light client can't validate a full block because he doesn't have the blockchain detail, which is required to validate transactions. And we also like to support larger blocks. So it's not something, downloading full blocks all the time isn't something we'd really like to do. Although there is work ongoing on wallets that do it that way, which is good work. Compact block invalidity proofs or fraud proofs. There's a lot of focus on that, probably mainly because Satoshi mentioned it, which would let a wallet detect a hard fork or invalid, something that was invalid. Detecting that situation where the blockchain is invalid itself isn't the subject of this talk. The subject of this talk is much more mundane and easy. The subject of this talk is how do we build a scalable payment verification network based on the fact that light clients have such minimal requirements compared to full node clients. Well, the first things first, and that is let's think about the things we're not doing in these light clients. The two primary ones being Android Wallet for Bitcoin and Bread Wallet for iOS. There are many others. One thing they don't do is they don't fetch input proofs. They don't check whether the coins that are being spent are connected to the blockchain. And they could do this with the support of the Bitcoin nodes. They don't check for spentness proofs. They don't ask the nodes, their peers, to tell them when money that you receive has already been spent, either in a block or in another unconfirmed transaction. We could do much better on that front. It requires cooperation between the SPV wallets and the full nodes. In our Bitcoin XT project, this is something we've made just a little bit of progress on. And with the first two things, the SPV wallet could also add much more complete local transaction validation rules. In the example on the previous slide, there was a $2 million payment received. Once you have the inputs, you can check whether you've spent more than is in the inputs. So this is something that really ought to be done. There's also a number of network practices that can be improved in the peers, and the wallets are working on this. You can split filters among peers. That improves the privacy problem. You don't have to send all of your addresses in a Bloom filter to all of your peers. You can do peer rotation where you don't stick with the same ones all the time. You can enable the use of trusted peers. There's work going on that in Bitcoin Core, and if that's an option that's available to you. Also, the Stash project isn't SPV per se, but similar. It involves running a trusted peer. These are all things we can do to make light wallets more secure. Also, we could explore the use of Tor to reach the P2P network, so that you can be more sure that you're actually talking to it and not to your network provider running some kind of a proxy. Improving SPV security, just to present it graphically, your wallet would like to see everything on the diagram in the next slide. The one I'm showing you now is what you get today, and that's two things: the payment transaction itself that you've received, and if you spent it, or maybe you have another wallet that spent it, you'll receive the fact that it's been spent. But what you really like to know is quite a bit more. This M in this SP input spend proof slide is the orange one. Is connected to all its inputs, some of which are in the blockchain, some of which are in the mempool only. So this one is kind of a worst case scenario. It's also depending on unconfirmed transactions, which are too deep. You'd like to receive copies of all this stuff. Also, in this trumped up example, the transaction that pays you is relying on an input C1 that's already been spent, and that could be told to you and proven to you by your peers. It also depends on an unconfirmed input that happens to already be double spent, which you could find out about, and you can find out about in real time when it happens. No reason not to try to do this. Not the same as saying it works perfectly every time, but right now we're not trying to do this at all, really. So those are security improvements that can be made. Now with these improvements, we need some support of the network to make it happen. The original Bitcoin network was everybody was a miner, a node, and a wallet. Today's Bitcoin network, the mining function has specialized significantly, and wallets, the SPV wallets I've been talking about, are in the millions, and nodes are in the low thousands. So you have a sort of a three-tier network. Some people run a wallet with their node. Other people just run nodes. And many people just run light wallets. But what we need, or what we could build, and this is a talk of ideas. This isn't something that's implemented or even really designed. This is a high-level sort of architecture that might be used. I represented by this triangular node picture the idea of a light node whose purpose in life is to serve SPV wallets and nothing else. An SPV serving node like this only needs SPV security itself, because the wallet can't tell any different. And I envision it having three capabilities. And these are sort of a la carte. You could have some doing one of these three functions. Some might do them all. There's a prover. This would provide the input and spentness proofs. And it would do it for, I'll talk about it more in a second. There's a prover finder, which helps you find the right nodes that can help you. And there's a transaction repeater, which you need to talk to get forwarded your transactions. The prover provides input spentness proofs for a TXID stem like 828 FEA or some other arbitrary length or configurable length stem. And so it has the job of maintaining a blockchain shard set by TXID stem, so that when it's routed to and it's asked to provide an input proof, it can do so. And it also knows which pieces of the blockchain to store in its shard as it sees traffic come from full nodes, new blocks and transactions. It registers the stems that it serves with the next class of nodes called prover finders. And collectively, with these provers, it approximates the function of a single full node, although it's much more has much more capacity than a single full node, because you have the power of all those partial nodes. And it could validate anything. It could provide input proofs and the associated spent proofs for anything. Something I didn't mention earlier but was on the slide is that what an input proof, once you have it, it ties your coins to the blockchain. A spentness proof is probabilistic. What you can do is you can ask as many nodes as you think you need to prove to you that the coins you're being paid with are already spent. And if they fail, then you would conclude that they are not spent and that your transaction can be trusted. So what you would definitely be able to do is, if you are able to obtain a spent proof, you could turn the transaction red if you know that there's something wrong. Whether you turned it green would depend on, or what color you might turn it in the UI of your light wallet, would depend on how many nodes you asked and failed to get a proof of spentness. And of course that can change at any moment, so the real-time nature of it is very important. SPV wallet users rely on unconfirmed transactions, so any improvements or networking or otherwise that are made in the future need to take the needs of unconfirmed transactions into account. Specifically, ideas like TXO commitments, while they may work terrifically, none of those ideas, all of those ideas are pointed at reducing the effort in proving spentness or unspentness of confirmed transactions. Unconfirmed, you need something like this that's a lot more real time. And collectively they can validate everything. The prover finder, this is the one that I've thought about the least. And part of that is because it's really something we've seen before. It's a DNS-like service where you would broadcast or send to your configured finders, just as you would to a DNS server, which stems you're looking for to ask for a proof of. So if you get a transaction with 3 inputs, and so it would have 3 different stems likely, you'd be looking up 3 different nodes to ask for input proofs from. And this could be partitioned hierarchically, just as the DNS network is. And actually using DNS, to me, is a likely solution because it's very, very similar. You would just need to, and you could contact the finder, and who would then tell you where the prover was, and you talk to the prover directly. Now, when I say you, I'm talking about the next thing I'm going to present, which is the concept of a transaction repeater. A transaction repeater is sort of the SPV wallet's main partner. You need to have one of these. He's going to host your Bloom filters, and he's going to look out for transactions that pay you, or that you're otherwise interested, that otherwise match your Bloom filter, or the subset of a Bloom filter that you decide to give one of your several repeaters, which is more private. And so it's the repeater that would be a prover finder client. So in other words, the prover itself, or prover finder, wouldn't necessarily know which inputs you were looking up. It would be a two-hop. It's both more efficient and more private. So the transaction repeater, not to get into jumping down the list too much, it hosts your Bloom filters. It relays the transactions. In order to do that, to host arbitrary Bloom filters and relay transactions to the SPV clients who register those Bloom filters, it has to see all the transactions. So the transaction repeater would see the full transaction flow, just as a full node does today. So it needs to have bandwidth similar, but it's not validating. So it doesn't have to have the blockchain. It doesn't have to do all the work of processing blocks. It basically is a repeater, and it decentralizes the Bloom filter hosting as well as scaling that function. So these three things put together, the next slide is a representation of what you might call a scalable payment verification network, where there's a lot of these mixed in with a lot more wallets. Maybe there's 1 billion wallets. We'd like to get to where everyone could run a wallet, or at least shoot for that. There are, and along with the full nodes and mining nodes, there's quite a few of the partial nodes whose job is to serve the SPV wallets. This network, which contains a lot of the SPV light nodes, has the properties listed on the last slide here. It can maintain an increased transaction rate with maintained decentralization. That's because you don't have to run a full node to participate meaningfully in the security of the network and contribute to the security of the network as one of these light node runners. That's the question: is how can people want to run full nodes, but if it gets more expensive, and it's going to get more expensive, the only question is how much more expensive it's allowed to become. If there's a way to run a light node where you're doing a little bit less for the network, but lots more people can do it, that could work. The SPV, second point in the SPV network, provides increased light wallet security, as detailed in the first half of the talk here. And then what we don't need to do for any of this is make any consensus changes at all. There's no hard forks. There's no soft forks. These are networking changes. There's no changes to transaction authoring or acceptance. This is all the same. There's no crypto changes. I'm kind of contrasting it with some of the other scaling solutions. There's no capital funding required for hosting a wallet, per wallet hosted. In other words, to turn on and plug in, no one has to front you money, which is one of the things that is going to have to happen with the Lightning Network. No cosigners are necessary. This distinguishes SPV from green address and other and Lightning Network and anything else where you're participating in multi-sig with a third party. Not necessary. There is a lot of work to be done, although these things are these ideas are not groundbreaking and are things that we've done before as an engineering community, there's a lot of work to be done, and figuring out how to do it incrementally is the next point. Is very important. To that end, the prover and all three pieces really, or two of the three pieces, not the prover finder, which is totally new, but a full node can be a prover for all the transaction space, and a prover is a repeater. It does all those things that the repeater would do today. It doesn't have to look up provers because it can prove everything because it's a full node. So the incremental building can be done by adding capabilities or support for slightly new protocols within current full nodes. And lastly, this capability, this scalable version of the SPV serving network isn't even needed right now because connection slots for SPV clients are not at a premium, even with the number of full nodes we have today. And we probably haven't exhausted the number of SPV wallets that could be served by just finding more innovative ways of adding full nodes. But once we exhaust that, and depending, of course, on adoption rates, something like the scalable network described here is going to be needed to support scaling to a truly large number of SPV wallets. And I'm optimistic as far as what can be accomplished along these lines. Okay, that's all I had, and I'd be happy to take some questions.
Okay, I have a question. Anthony is asking, do you envision these new types of nodes serving SPV wallets being incentivized for the services they provide, e.g. using some sort of payment channel? I think it's a great idea. One of the it wasn't part of. I think people do want to contribute. It's just going to get more difficult as it gets more expensive to get enough people to contribute voluntarily. But I saw a great idea when the 21 came on the scene and had their decorated Python methods and ways of creating a Bitcoin service. Somebody said, "Hey, why don't we just put that in front of a full node and just charge for everything it does?" And so it seemed that I thought was a really neat idea because you could it would be pretty easy to do. It's almost like device driver level development where you're just matching up two things. But yeah, it's been, you probably know, Anthony, that there's been a bunch of ideas about how to do that, and so far it hasn't. None of them have really caught on. But if someone could figure that out, I do think that'd be a big enhancement.
Well, thank you very much for your time today, Tom.
Thank you.